All right, verifying inverse functions. We've kind of talked about this, but let's go through how to do this algebraically and mathematically. Oh, and here's just a very pretty picture of cherry blossom trees. Yeah. Okay, so verifying inverses graphically. We've talked about this, but the graph of f of x and f inverse of x are symmetric across the line y equals x. Okay, so that means that they are mirror images over that line. Okay, so in order to verify if two functions are inverses graphically, you just verify that they can reflect over the line f of x equals x. Okay, so if I'm given 3x minus 6, and I want to graph this, well, we can just graph it using mx plus b. So our b is negative 6, so that's where we cross the x-axis. And then the slope is 3, so I'm going to go up 3 over 1, up 3 over 1, and there's my line. Okay, now I need to find the inverse of this. So, and the other way, so if you don't know how to graph something, you can always just make a table of it. So if I plug in negative 2, I'm going to get out negative 12. Negative 1, I get negative 9, 0, negative 6, 1, negative 3, 2, 0. And you can just keep plotting points until you get to the points that you want. Okay? So if I find the inverse, we have y equals 3x minus 6, which is x equals 3y minus 6. If I switch those, solve this. So add the 6, divide by 3. So I have f inverse equals x plus 6 over 3, which is really the same as 1/3 x plus 2. So that means I'm going to cross the y-axis at 2, and I'm going to have a slope of 1/3. So up 1 over 3, up 1 over 3. Now, to verify this, I just need to put in the line. Oh, yeah. And again, you can just plot points and graph the points. But I'm going to put in that line right there. That does reflect over both, so I just verified it. We're good. Boom. Okay. This one, so f of x equals x cubed plus 4. Now, if I graph this, so I'm going to go, that means we're moving the cubic function up 4. So I have a y-intercept right there. And then if you think about the cubic function, so x cubed, I can make a t-chart of just x cubed. So this would be, this is my x, this is my y. So negative 2, negative 1, 0, 1, 2. Well, if I plug negative 2 and I get negative 8. Negative 1 and I get negative 1, 0, 0, 1, 1, 2, 8. So this goes, I have a 0, 0, negative 1, negative 1, 1, 1, and then negative 2, negative 8, and 2, positive 8. So this looks like this. Now, if I want to graph that over here, I can just do the same thing, but this would be my starting point. Okay, so I'm going to go left 1, down 1, right 1, up 1. Then I'm going to go left 2, down 8. So 1, 2, 3, 4, 5, 6, 7, 8. And then right 2, up 1, 2, 3, 4, 5. That's like up here somewhere. Okay, and then this could just graph like this. Okay, or you could plot points and do it that way. Either way is fine. But there's that graph. Now I need to find the inverse. Find the inverse, sorry, I got distracted. So y equals x cubed plus 4. Switch the x and the y's. Subtract the 4 and cube root it. So f inverse equals the cube root of x minus 4. Which the cube root of x minus 4, well, that x minus 4 moves this right 4. And now it's pretty much the inverse of, well, it is the inverse. Cube root of x is the inverse of x cubed. So if this one goes like this, well, the cube root, if I just switch these values, that's what this is doing. So negative 8, negative 2, negative 1, negative 1, 0, 0, 1, 1, 8, 2. So from this point, I could go back 1, down 1, here, here. But then I could go back 1, 2, 3, 4, 5, 6, 7, 8, and down 2. And right 8 and up 2. So it's going to be like right there. So this is going to look like this. Okay, and again, if you don't know how to do that, just graph it, or just plot the points. Okay, and I know I left these like this. It's because when I made this, I didn't have a calculator, but you can just find decimal equivalents to that, okay? Now here, that does reflect over that line, so we're good. Cool? So now, to verify algebraically, if you can think back to the beginning of the year when we did function composition. So that was where we had like f of g of x and g of f of x, where basically this means, so if I have f of g of x, so I am going to take f of x, or x, and plug it into g, and then plug that g of x into f. So like this right here is really saying f of g of x. So I'm going to take whatever g of x is and plug it in for the x value in f. And this is saying, well, g of f of x, I'm going to take the f function and plug it into g. Okay. So verify algebraically that these two are inverses. So I'm going to do f of g of x, which is really just f of g of x. So I'm going to plug g of x into f. So that's going to be f of 2x plus 7, because that's what g of x is. So that's going to be 2x plus 7 minus 7 over 2. I'm just going to get rid of those parentheses. So these 7s are going to cancel, and I have 2x over 2, which now the 2's cancel, so I'm just left with x, which is what I wanted. So to verify these, f of g of x must equal x, and g of f of x must also equal x. Okay, if you end up with something other than x, it's wrong. Halfway there, okay? So now we have to do it the other way. So I'm going to do g of f of x, which means I'm going to plug in x minus 7 over 2 to that f of x function. So that's going to be 2 times x minus 7 over 2 plus 7. So those 2's cancel. So I'm left with x minus 7 plus 7, which is just x. We did it. Okay? You have to show all of this work when you're doing it. If you do not show all of your work, no points. Okay? Let's do this one. So if we want to verify this, I'm going to do f of g of x first. So I'm going to plug in the square root of x plus 5 into that function. So I have the square root of x plus 5 squared minus 5. That square gets rid of the square root, so I have x plus 5 minus 5, which is x. Now if we go the other way, I'm going to plug f of x into g. So I'm going to plug x squared minus 5 into the g function. So that's going to be the square root of x squared minus 5 plus 5, which is I'm just going to get rid of those parentheses. Those 5's cancel. I get the square root of x squared, which equals positive or negative x. Now, this positive or negative is an issue for us, okay? We cannot have a positive or a negative. It needs to just be x, which means that, hold up, these are not inverses. If we restrict the domain, they are. So if I say so, because if I was to graph like the x squared minus 5, this just goes down 5, 1, 2, 3, 4, 5, so it's right there. If I was to say that, okay, let's just ignore the left side of this. And let's say that x is greater than or equal to 0. Then these are inverses. But since I did not state this, that means that these are not inverses. Okay? All right, so now let's just put it all together. So we need to find the inverse of each function and state any restriction to the domain, and then verify graphically and algebraically. So this cube root of x plus 2, let's graph it first. So that x plus 2 moves it left 2, and then I can plot those points, kind of the same as I was doing before. Or you could just make a table here. Okay, I don't care how you do it really. But then I'm going to find the inverse, so y equals the cube root of x plus 2. Switch those, x equals the cube root of y plus 2. Cube both sides, so I have x cubed equals y plus 2. Subtract the 2. X cubed minus 2 equals the inverse of x. Now if I graph this, I'm going to go down 2, and then plot those points. There's the inverse. And they do reflect over that line, which means that, yep, we have verified it graphically. But we still need to verify it algebraically. So f of g of x is the same thing as f of g of x. And then I'm going to plug the x cubed minus 2 into that. So I have the cube root of x cubed minus 2 plus 2. The 2's cancel. I'm left with the cube root of x cubed, which is x. Do it the other way. So I'm going to plug the cube root of x plus 2 into that function. So that's going to be the cube root of x plus 2 cubed minus 2, which is x plus 2 minus 2, which is x. Booyah. Okay. Now this one. So if I want to graph this, I just plotted a bunch of points. Now I know that, so 5 over x, that's going to give me an asymptote at 0. So x can equal 0, and then that plus 2 is going to move this up 2. So that means that we're going to have a horizontal asymptote and a vertical asymptote. And I didn't draw these on the graph, but that means we have a horizontal asymptote right here and a vertical asymptote right here. Okay. But then I need to find the inverse. So I'm going to switch my x and my y's. And then I'm going to subtract 2, multiply by y, and divide by x minus 2. So I have 5 over x minus 2, which now this one's going to have a restriction of x can't equal 2. So my inverse has a restriction of x can't equal 2. And then again, I just plotted points. There's my points, and there's my graph. Okay, plotting points. If you don't know how to graph something, always plot points. Okay? You did it. Almost. We still need to verify this. So I do f of g of x. So I'm going to plug 5 over x minus 2 into the f function. So that's 5 over 5 over x minus 2 plus 2. I'm going to rewrite that as a division. Now you can always flip and multiply. So that's 5 times x minus 2 over 5 plus 2. The 5's cancel, and I'm left with x minus 2 plus 2, which is x. Okay, so if I have g of f of x, well, then I'm going to plug 5 over x plus 2 into that function. So that's 5 over x plus 2 minus 2. Well, those 2's cancel, and I'm left with 5 over x. Write it as a division, so 5 divided by 5 over x. Flip and multiply, so 5 times x over 5. The 5's cancel, and I'm just left with x. And we did it. Okay? I think this is the last one. So if I have the square root of x plus 3 times 1/2. So that plus 3 is going to move it left 3. And then typically with the square root function, so we have our x and our y. If I plug in like 0 to my, this is the square root of x, I would get 0. But then if I plug in 1, I'd get 1. If I plug in 4, I'm going to get 2. And if I plug in 9, I'm going to get 3. Or like 16, you get 4, and you can keep going with this. But since this is being multiplied by 1/2, and I'm going to treat this as my 0, 0, I'm going to multiply all these by 1/2. Okay, so 0 times 1/2, well, that's that point. And then I'm going to go over 1, up 1/2, that's like right there. Over 4, 1, 2, 3, 4, up 1. And then over 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, up 1.5. So that is going to be it's almost flat. But that is what that looks like. Okay. Or just plot points, which is essentially what I just did. Okay. So then if I want to find the inverse of this, switch my x and my y's. I'm going to multiply by 2. So I get 2x equals the square root of y plus 3. Square both sides, which that's really just 4x squared. And then I'm going to subtract the 3. So I have f inverse equals 4x squared minus 3. Now, if I was to graph 4x squared minus 3, it looks like this, right? But anytime you have a square root function, this is not going to be the inverse of this. So I need to ignore the whole left side of this. And that is what it is. So I do have a restriction on my domain. It's x has to be greater than or equal to 0. If you graph it, it looks like that. Okay, and so that does reflect over that line, so we're good. And now we're at the halfway mark. So I need to verify this algebraically, so I need to plug in f, or g of x in the f function. So I have f of 4x squared minus 3, which is 1/2 times the square root of 4x squared minus 3 plus 3. Those 3's cancel. I get 1/2 times the square root of 4x squared. Well, the square root of 4x squared is 2x, so 1/2 times 2x. The half and the 2 cancel, so I'm just left with x. We can do it the other way, so g of f of x, which means I'm going to plug f of x into the g function. So that's g of 1/2 times the square root of x plus 3, which is 4 times 1/2 times the square root of x plus 3. That's all squared, minus 3. Well, if I square the 1/2, I get 1/4. And if I square the square root of x plus 3, I just get x plus 3. Now, the 1/4 and the 4 cancel, so I'm just left with x plus 3 minus 3, which I'm just left with x. Okay? Cool. I'm done. Goodbye.